Medical AI models routinely achieve exceptional diagnostic accuracy in controlled testing environments, yet most of these systems stall at the threshold of clinical adoption. The friction usually originates at the executive level. Development teams build a model optimized purely for predictive performance, and leadership treats trustworthy AI as a retroactive compliance checklist to complete just prior to deployment. Auditing a finished model for bias, safety, and transparency after it is already built is structurally ineffective. Under incoming global regulations, deploying systems designed this way exposes the organization to massive legal liability. The AI Prognosis Project, a major European research initiative developing predictive models for Parkinson's disease, provides a clear case study on how to solve this bottleneck. Instead of evaluating an opaque model at the end of its development cycle, the consortium shifted their approach. They embedded ethical safeguards and rigorous transparency checks directly into the engineering pipeline. To survive regulatory scrutiny and ensure actual adoption by physicians, trust cannot be an add-on feature. It must be engineered into the system architecture from day one. To understand why AI models fail in the real world, the AI Prognosis Project conducted an internal survey of its own data scientists and developers, asking them to rank the importance of various AI governance requirements. This heat map illustrates the results. Technical teams inherently prioritize system proximal metrics. Accuracy scored an 8.4 out of 10, and privacy scored an 8.0. Developers focus on the immediate functionality and security of the code. However, looking at the expanded chart, macro-ethical concerns drop significantly. Bias mitigation hovered around a 6.5, while societal impact received a 4.7. This happens because developers are optimizing for immediate technical constraints. Working under strict delivery deadlines, they produce models that run efficiently and predict accurately. In that high-pressure environment, macro-level societal impacts feel diffuse. They are treated as abstract philosophical problems outside the immediate scope of software engineering. This creates a severe executive risk. The engineering team delivers a mathematically flawless algorithm that contains massive structural blind spots regarding fairness and clinical usability. If leadership fails to actively bridge this gap between technical execution and clinical reality, the resulting models will inevitably face regulatory rejection. Optimizing clinical AI requires managing a zero-sum game of competing technical and ethical mandates. Pushing one metric higher often directly degrades another. This slider demonstrates the first major trade-off. You can build a highly accurate, complex neural network that operates as a black box, or you can build a highly explainable logic model that sacrifices predictive power. Tracking progressive conditions like Parkinson's disease across thousands of variables requires high-dimensional neural networks. The system needs complexity to find subtle patterns in the patient data. But an opaque model is useless in a hospital. A clinician cannot formulate a treatment plan based on a machine's output without a clear, intelligible rationale confirming why that specific diagnosis was made. The second major trade-off occurs during data collection, complying with strict privacy laws versus ensuring algorithmic fairness. This graphic shows patient data passing through a privacy filter. Strict data minimization protects the patient by anonymizing their records, but it simultaneously strips away the demographic markers required to test the model for racial or socioeconomic bias. Organizations are forced into a difficult position: violate patient privacy protocols to collect demographic data, or launch a model that cannot be mathematically proven to be fair across diverse populations. Executives cannot permanently solve these tensions. Instead, they must build procedural frameworks capable of governing these trade-offs dynamically across the entire lifespan of the product. To manage these overlapping requirements, the AI Prognosis team applied the Assessment List for Trustworthy Artificial Intelligence, or ALTI, framework. This diagram outlines their solution. They mapped the 7 ALTI requirements across a 6-stage engineering lifecycle, translating abstract ethical principles into a concrete operational roadmap. In the initial design stage, the ethical requirement for human agency translates directly into defining technical fallback mechanisms and system overrides before a single line of code is written. Moving to data preparation, privacy and fairness mandates require engineers to implement strict data quality routines and conduct reviews specifically designed to catch hidden proxy biases. During model development, the requirement for technical robustness means engineers must build adversarial stress testing pipelines to interrogate the algorithm's behavior under noisy or uncertain conditions. At the UI/UX stage, transparency dictates the interface design. The dashboard must communicate probabilistic risk and model uncertainty directly to the clinician in a clear, digestible format. For external validation, the team evaluates the model's performance across highly heterogeneous populations and varying clinical settings to empirically prove fairness and generalizability. Finally, in the governance stage, engineers deploy MLOps pipelines and strict version control to ensure the continuous monitoring of the system's societal impact and accuracy drift over time. This process eliminates ambiguity. It forces development teams to treat ethical guidelines as trackable, verifiable engineering realities. Adopting this 6-stage procedural blueprint is an absolute mandatory organizational capability for scaling medical AI today. Relying on procedural scaffolding is the only documented method proven to scale complex clinical AI systems, from the laboratory to the hospital floor. This operational efficiency is now colliding with an immediate commercial reality, the newly enacted European Union AI Act. The AI Act legally enforces this type of procedural governance for all high-risk medical systems entering the European market. We can map ALTI pipeline controls directly onto specific legal mandates. The mechanisms engineered during development, like adversarial robustness testing, structured human oversight, and dynamic model documentation, legally satisfy the EU AI Act's strict requirements for continuous post-market surveillance under Articles 14 and 29. By adopting these mechanisms early in the design phase, organizations guarantee continuous data quality while shielding themselves from massive compliance bottlenecks later. Translating ethical mandates into embedded engineering workflows transforms a heavy regulatory burden into a severe competitive advantage, clearing the path for rapid market entry. Trust in clinical AI is a living system. It must be engineered deliberately, cultivated carefully, and rigorously governed across its entire lifespan.